In this video, we will explain some counting principles. Let me start by saying that if we have two sets, let's suppose that this is the set A, B, C, and we have the set B equal D, E, A, then we can see that the union of these two sets is the set A, B, C, D, E, and the intersection of these two sets is equal to just the set whose only element is A. And then we can see that the number of elements in the union, let's denote this by the number of elements in the union, it's going to be 5, but the reason of that 5 is because it is the number of elements in A plus the number of elements in B minus the number of elements in the intersection. And essentially, when I do the sum of the number of elements in A plus the number of elements in B, I'm doing 1, 2, 3, 4, 5, 6, but some of them I am overcounting. I'm counting them twice. Which one is it? Those in the intersection. A, I'm counting it twice, then I have to subtract that. Then we have this formula that works in general when we have two sets. And let's call this formula number 1. Another one is that if we have, let's say, the set D equal 1, 2, and E equal to 1, 2, 3, and F equal to, let's say, A and B, then if we do the Cartesian product, A cross E cross F, then we will end up with the number of elements of the Cartesian product is going to be 2 times 3 times 2. And let me just remind you what are the elements in this Cartesian product. And here we have like 1. And let's take care of everything that starts with 1. 1, 1A, 1, 1B, 1, 2A, 1, 2B, 1, 3A, 1, 3B, and then this is everything that starts with A. We have 1, 2, 3, 4, 5, 6, because 3 times 2 is 6. But then we have to do the same, but starting with 2. Then we have 2, 1A, 2, 1B, 2, 2A, 2, 2B, 2, 3A, and 2, 3B. And this is the Cartesian product, and in this case we have 1, 2, 3, 4, 5, 6, and another 6, we have 12. And we can generalize this as saying that the number of elements in the Cartesian product of K sets is just the number of elements in the first set times the number of elements in the second times the number of elements in the last set. And we have this formula. And let's call this formula number 2. An example of this formula helps us to describe the outcomes in an experiment. Let's suppose that we have a quarter and a dime, and we toss those two coins. Then in this case, the possible outputs, let's say for the quarter is head or tail, and for the dime is either head or tail. Then when we do the Cartesian product of these two sets, we get that the number of elements here is going to be the number of elements of Q times the number of elements of D, and it's 2 times 2, which is 4. And then the outputs are ordered pairs, head, 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 tail, tail, head, and tail, tail. Something that we usually are going to do is to identify an ordered pair, let's say head, head, with this expression, like if this were a word. Right? HH is going to have the same meaning of the ordered pair, HH. Notice that somehow it makes sense, because if we have head, tail, then we are going to think about this word, but tail, head, we're going to think about this word, and we are used to words, and these two words are different in the same sense that these two are different. Then sometimes we're going to be denoting this just like head, 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 tail, tail, head, and tail, tail. Same thing happens for when we have a triplet. For example, for a triplet, we're going to have like 1, 1, A. We're going to identify this with 1, 1, A. Right? We can think of this like a license plate, right? 1, 1, A. And notice that it is different than a set. If we think about the set 1, 1, A, this as a set is the same as the set 1A, and is the same as the set A1. Then we use ordered pairs or triplets or n-tuplets when we are taking into consideration the order, and sometimes we are going to replace just those by words. Right? And sets are different. Right? When we think about a set, the order doesn't matter. Let me erase everything. We have a very nice generalization of this formula. Let me just rewrite the formula, that the number of elements of the Cartesian product is equal to the number of elements of A1 times the number of elements of AK, and it's called the basic counting principle. And it says that if we have an experiment, and that experiment can be divided into stages. They say we have an experiment, and it can be divided into K stages. Then for that experiment, if we know that the first stage, we can have, for the first stage, we can have N1 possible outcomes. And this is important. For each outcome of the first stage, we can have N2 possible outcomes in the second stage. We have N2 outcomes. And for each combination of possibilities in the first stage and the second stage, we have that in the third stage, we have N3 possibilities or N3 outcomes. And if we continue like that until we get that for the kth stage, we have NK outcomes. Then the number of possible outcomes in this experiment is going to be N1 times N2 times NK. Notice that our previous example fits into this. We have that the experiment consists in tossing 2 coins, a quarter and a dime, and we have that for the first possibility, we have either tail or head. We have 2 possibilities, and for the dime, we also have tail and head. And then the number of possible outcomes is going to be 2 times 2. Sometimes it's very useful to use a tree. It's called a tree diagram to represent these experiments. For example, for this experiment of tossing a quarter and a dime, we can draw this. This is the beginning, and then we have, this is a stage 1, and we have either head or tail, and for each one of these we have either head or tail or head or tail, and this is a stage 2. And the final set is going to be head, 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 tail, tail, head, and tail, tail. And in this case, the set describes all the outcomes of the experiment is going to be head, 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 tail, tail, head, and tail, tail. And remember that we are identifying, in this case, these words, in the sense HH is considered like a word, with a like Cartesian product. Then this is just HH, HT, TH, and TT, which is just what we denote in the previous example as Q Cartesian product with D. This formula is a particular example of this, but this is a little more general. Let's do an example that shows that this one is more general than just the Cartesian product of some sets. Let's suppose that we have 3 letters available, A, B, C, and we want to count all the possible words with 2 letters, but the letters must be different. Some examples are AB or AC or BC, but notice that the word AB and BA is different, and the word AC and CA are different, and BC and CB are different. We can model this experiment using the basic counting principle. We can divide this into stages. Let me do a tree diagram. In the first stage, we're going to select the first letter. And then for the first letter, we can select either A, B, or C, and we're going to call this stage 1. For the second stage, we know that we only have 2 possibilities. Why? Because once we have selected a letter, since we want the letters to be different, then I only have 2 possibilities. Here, if I select A, then the possibilities are B and C. If I select B, the possibilities are going to be A and C. And here, if I select A, the possibilities are going to be A and B. And the final result is going to be AB, AC, BA, BC, CA, and CB. Let's get used to denote the set of possible outcomes. By the way, the set of possible outcomes is going to be called a sample space of the experiment. And sample space of an experiment. Then the sample space is just a set that describes all the outputs of an experiment. Then in this case, the sample space is going to be AB, AC, BA, BC, CA, and CB. This is a sample space, and this is an example in which the experiment can be modeled by stages. The first stage has 3 possibilities, and the second stage has 2 possibilities. In this example, N1 is 3, N2 is 2, and K, which is the number of stages, is 2.